Okay, so let's pick up where we left off. All right, so in the previous class, we were basically talking about different types and classes of naval vessels. And most of the normal ones that we are familiar with are hydrostatic support hulls. Some more exotic ones are hydrodynamic support, where you have hydrofoil that helps you lift the hull out of the water. And very rarely we see hulls that use aerostatic support. Okay. And the next thing that we need to talk about is load lines. So anytime you've looked at the side of the hull of a huge ship, you've probably seen markings like this. And they're actually useful to determine what level you should load your ship to. All of these are short form for this. F means freshwater, T is tropical, summer, winter, and this is tropical freshwater. So these lines are basically saying it's safe to operate your ship at these water levels in the different conditions. Okay. Now think about why this is necessary. Why would you care about what the level is in winter waters versus in tropical freshwater? What changes? What changes? Salinity changes, yeah, a little bit, but going from New England to, let's say, going to, what's a good tropical destination? The Caribbean, okay? Temperature is the main thing that changes. Temperature changes, what happens to the water? Or anything, water, air.
Density change.
Density changes, yes. Cooler water is more dense, and as you expect, warmer water will be less dense. So, fine, density changes. How does that impact our ship? What level the water line is at? Nothing else will change, so the cargo load is the same, fuel capacity is the same, but the water level, you'll see changes depending on the temperature of the water, meaning density. So why? Okay, you told me density changes, fine. Think about buoyancy. What happens? I told you the weight of the ship doesn't change. You have the same amount of cargo, the same fuel load, same amount of people. So the weight acting downward is the same. What about the force supporting that weight?
The force is proportional to the volume of the water displaced, or the weight of the water displaced, which is proportional to the density.
We can barely hear you. My volume is very low. Can you say that once more?
Okay, the buoyant force is
still can't hear you. Okay, give me 1 second. Okay.
The buoyant force is proportional to the weight of the water displaced, and that's proportional to the volume of the water displaced times the density. So it's proportional to the density.
Yeah, so that's exactly the reason. When the water is less dense, you need to displace more of it because the weight will be lower if you displace the same amount of volume. How do you displace more water? Your ship sinks a little bit, okay? So look at the markings. If you start sailing at this level from New England, you just keep going and you'll see the ship changes its water line to this. So does it make sense? As it starts sinking, it's displacing more water. Weight of the water depends on volume and density. Density is lower, so you need to displace more volume. All right? So that's the main purpose of this. This also helps you ensure that you're in charge of loading the ship. Let's say you load it in the Caribbean, you can load it up to this level, all right? And it basically ensures that no matter what location the ship goes from that point on, it'll be safe, okay? If you didn't take this into consideration and say you loaded up to the maximum level here, starting from New England, as you sail to the tropics, the water line will keep going up and your hull might hit the seabed in shallow waters, okay? So it's to prevent all of that from happening. These letters NV are basically what it indicates the specification or the registration of the ship. All right. Lloyd's register you might have heard of. It insures many things. So if the waterline follows what Lloyd's register specifies it should, you see an LR marking. This NV is, I don't know. Let's see. I think I have it on the other side. Okay, wait, let's go one more. No. Okay. Yeah. I don't remember what NV is. But there's many. BV is Bureau Veritas. There's a few more. I have a list later on. I'll show you. All right. So a few more terms. Deck line is basically once your water level rises above the deck line, you're flooded. So you never want to go over that. Freeboard is a term you use to describe the distance from the deck line to the water line. Okay, so this is the summer freeboard. You see the summer water line would be here. The tropical freshwater freeboard would be this much. Okay. Yeah, so this is just showing what we just talked about. The load line allows the maximum legal limit. You can, of course, load it lower than that, but then you're not carrying as much cargo as you could. All right. And yeah, so you can load it up to this level, not beyond that. Okay. Yeah, it's just the same things we just talked about. Buoyant force depends on density, which changes with the temperature. Okay, and this is the scenario that we were describing. When you're in cold water, your ship will ride high, and as you go to warmer waters, your ship will ride lower in the water. Okay. Low density, lower buoyant force, less load can be carried safely. Well, if you stick to the water lines, you carry the same amount of load in warm water or cold water. So I should remove that part. High density, high buoyant force, again, ignore the more load can be carried safely. All right, again, same thing we talked about. The ship could go through all of these different temperatures on the same voyage. So the water lines help us make sure nothing bad happens. Okay, ordering makes sense now. Why? Tropical freshwater is on the top. Winter North Atlantic is on the bottom. Yeah, good. All right. Okay, fine. All right. So then we continue. Okay. These are some, let's say, standards that different agencies specify for what the distance between all of these markings should be. So the winter freeboard should be T over 48 larger than the summer freeboard, meaning that's just telling us what's the distance between S and W. T is the draft. Do you know what draft is? From the keel, so bottom of the ship to the water line, that vertical distance is called the draft. So everything is in proportion according to that distance. Okay, winter North Atlantic, 50 millimeters. Okay, and now this is not draft anymore. Tropical freeboard is 2T over 48 less, etc. You don't need to memorize any of this. I mean, based on the specification you choose, these values will be given to you. Okay. Here. So BV is Bureau Veritas, Lloyd's Register. RI is the Italian registration agency. AB is American Bureau of Shipping. And all of them have similar but slightly different requirements. All right. When a ship is when it's floating, does it make sense that the volume, well, the displacement is only associated with the part that's submerged? But it has to be dry. If you have, let's say, a ballast tank and you fill it up, that part is gone. You don't count that as contributing to buoyancy anymore. Okay? So any dry submerged volume contributes to buoyant force. This is basically density times acceleration due to gravity times displacement volume. All right. For an actual conventional hull, it's not straightforward to compute this, right? And we'll learn how to do all of this. So you see the cross-sectional area keeps changing from the aft as you go along to the fore section. And if you basically slice it up into many cross sections, each of them have different areas, and you basically have to use all of those to compute the total volume. Have you done this in fluid mechanics? Not for a regular hull? What did you do it for? A block of, okay. So Yeah, with blocks, it's easy, right? If it's rectangular or a parallelepiped, length times width times height. We can't do that anymore. So how would you do this now? If I gave you,
SolidWorks.
all right, SolidWorks. Integrals, okay. For doing this using integrals, what do you need? What's missing? I just give you the shape, the picture, you can't do it. What more do you need? The what? How do you compute area under a curve? What do you need? Yeah, you need the shape of the curve or the equation describing the curve so you can integrate it. So if I somehow figure out a nice function that describes the whole shape, you could start thinking about doing that, okay? But look at this, everything changes in all directions, in the longitudinal direction, in the vertical direction, and in the lateral direction. Okay, so doing this analytically is not very feasible. So as somebody said, you could use SolidWorks. How does SolidWorks do it?
The way we did it for senior design is that we create two models of the same AUV that we're using. One, it was solid with all the dimensions, properties of the materials that we need. The other one, we change all the properties to salt water. And then, so all the components of the second, design, everything was with the density of the salt water. With the mass properties, we see how much of force, buoyant force that design has. We compare it to what weight was on the system, and we figured it out how much negative or positive buoyancy we were and what we needed to do to accomplish our stuff. It's a little
Okay.
bit tedious, but it can be done.
All right. So you're basically describing the way you would have to do it. You'd have to go about setting up the compute calculation. But think about, what does SolidWorks do? It's a software, right? So it solves some equations. What does it do behind the scenes? It has to have some way of computing the volume or the area. What does it do?
It numerically integrates.
Yeah, it does integration as you mentioned. It just does it numerically, okay? Have you ever done numerical integration before? What class? Not for a class. You probably did analytical integration. So like if I say quadrature, do you understand what I mean? Trapezoidal rule. Okay, so you've probably seen it very briefly before. We'll use it very heavily in this class. So you do the same thing. You integrate to find the area or the volume, but you do it numerically. So that's what the computer program does, SolidWorks does. The only alternative is for it to find an equation that describes the hull, which is very, very complicated. But a much more straightforward way is to chop it up into pieces and look at individual pieces. So you could basically think of chopping this up into many, many tiny blocks. And these blocks are perfectly cube-like or rectangular shaped. And find the volume of each block, sum all of them up, you get a rough but very close approximation of what the total volume of this thing is. Okay, so that's numerical integration. All right, yeah, so this is basically the same thing. Buoyancy, effect on density, saltwater, rho S. Density of saltwater is higher than density of fresh water. So the force will be lower if delta is the same. If you want the force to be the same, delta has to be different. Delta represents, not delta, nabla. Nabla represents the displaced volume. Okay. I think we talked about this. Did I show you this before? No, okay. I think we were just talking about it. So did we talk about, I'm teaching another class, so I keep mixing up. Did we talk about submarines submerging? Okay, so the reason submarines can go underwater is because they take on water into the ballast tanks, okay? Otherwise, they'll just float like a regular ship or a tube full of air. That's what they are essentially. If you don't fill up the ballast tanks, this is what it'll look like. The weight of the equipment, of the people, of the fuel doesn't change as you go up or down. The only thing that changes is the displaced volume, okay? So if you're full of air, you'll float on the surface. But as you start filling up some of that dry volume with water, you lose the displaced volume. So you'll start sinking down, all right? How do you make sure, if you want your sub to, fine, you start at the surface and you need to go down. So you need to make sure your weight is larger than the buoyant force, okay? At some point you'll say, all right, enough, now I want to stop. What do you do then? How do you stop sinking? You've reached a depth of 30 meters, you don't want to go any deeper. What do you do?
You neutralize your buoyancy.
Can you say that once more?
You neutralize your buoyancy.
Okay, neutralize your buoyancy. You said start decreasing your weight. Okay, how do you start decreasing weight? Do you start throwing stuff off the ship or the sub? Yeah, you pump some of the water out of the ballast tank. So you restore some of the dry volume. And you need to do it just enough so the buoyant force is exactly balanced by the weight. If that's not the case, you'll either start rising up or keep sinking. Okay. Do you know that fish actually do this? They have like a sort of a bladder that they can fill up or shrink. That helps them either rise up or down. Otherwise, they have to keep flapping to go up, or when they could just expand the bladder and do that. All right. Okay. Aha. Have you heard of this one? Poop deck? You have? Okay, cool. So why is it called a poop deck? All right. Yeah, I didn't know this either. So let's see why. So it's this part in old ships. If you have seen models, that's called the poop deck. Yeah, here it's marked there. Okay. This is why it's called the poop deck. Pooper. So it basically comes from French. Okay, that refers to the stern of the ship. Okay, there was something else. The head. Have you heard of the head? Okay, why is it called the head? It's in the front. Okay, why is it in the front? Is it in the front on a boat? Is the head always, the head for people who don't know is the restroom. Okay, so why is it in the front?
Because in the old sailing ships, that's actually where they went to relieve themselves.
Yeah, that's exactly why. So old sailing ships, you always have the wind going, it has to fill your sails. So you want all the stuff to be up front. Okay, that's why it's called the head. All right. Okay, so some useful terminology. When talking about hulls, there are several different lengths we can talk about. The tip to tip length is called LOA, length overall. Okay. LWL, length on the waterline, is the red part indicates the wetted part of the hull. Okay. So from the aft, where you start at the wetted region and go all the way to the fore, that's LWL. Length between perpendiculars is what is used very frequently. So what this means, there's an aft perpendicular and a forward perpendicular. Okay, okay. I'll tell you where you exactly you locate FP and AP. So LOA you need to know, because if you want space to dock your ship, LOA is what's important. Okay. LWL, the length of waterline, determines stability of the ship. Okay. Actually, it's the area, but LWL is related to that. Forward perpendicular is where the bow intersects the waterline. All right. Aft perpendicular is not that well defined. The forward perpendicular is easy to spot, right? It's wherever your waterline is at the bow. Aft perpendicular, it depends. Okay, some people say it's where the stern intersects the waterline, so that would be all the way back here, or it's the rudder location, so somewhere here, or where the prop shaft emerges from the hull, so somewhere over here, or if the prop is very high up there. Okay, so the aft perpendicular depends on what your choice is. Looking at this, just the same things just from the top view. Okay, LOA, yeah, it's obvious. LWL. Can you visualize this again in your head? Anytime you look at these drawings, always try to think of the 3D structure. So, this is a uniform hull. This is not good. So, usually, if you look at a ship, the front part is curved. Okay, so that's the dry, unwetted part, shaded in gray. The wetted part is shaded in red. Beam is just maximum distance going port to starboard, any place on the hull, usually at the center midplane. Okay, that's the top view, that's the front view. Draft, that's what I was mentioning. T is goes from the keel to the water plane, to the waterline. Okay, that distance is called the draft. Depth is from deck line to the keel. So for a given hull, depth will not change, but draft will keep changing depending on your load or your operating temperature. Freeboard is what's left above the draft. Okay.
Wait, so in other words, the keel line is the total height of the top of the top of the boat to the bottom of its.
Not the keel line. The depth is the total height. Well, is the total depth. The keel line is just the imaginary line that touches the bottom.
Oh, okay, okay, okay.
Yeah. Okay. This is one of the most important things we'll use, water plane area. So depending on where the water line is at, this shaded area in red will keep changing. And the value of that AW determines a lot of different things. Most importantly, stability of the hull. Okay. Yeah, how would you compute this? So how would you compute the area shown in red here?
You would integrate again.
All right, you would integrate numerically, and so, no, not red. You would basically draw an imaginary x-axis. This is cutting the water plane area into two parts. It's mirrored, so we only need to worry about one part. And you start looking at what's the y value here. Oops, okay, what's the y value here? What's the y value here? Okay. You can take a tape measure and start measuring, right? So how do you, why did I draw these lines? How does it help in computing the area? What's a very crude way you could compute the area? Very straightforward way. Yeah, you just make rectangles here, right? So with these straight lines, you say this is my rectangle. Area of this is easy to compute. Area of that, easy to compute. Okay? So you see, if you do enough of these, you'll get the area of 1/2 of the water plane. What's the problem in doing this?
It's annoying.
If you do it manually, it's annoying, but you can very easily write a MATLAB program to do this, right? It's just a for loop going from box 1 to box 2 to box 3, etc. That's basically numerical integration. The problem here is you make a small error. See this part, which the small sliver is shown in red, should have been included in my area, but it isn't, okay? So that, yeah, there's no free lunch. When we make easy approximations, something gets missed. Yeah. Not in this room, in 250. Yeah, here it's fine. Yeah, thank you. Okay. Yeah, so what could you do to minimize this error that you make? What would you do?
Make them infinitely small or something? I don't know.
Yeah, make these boxes very, very small. So if you make many boxes, you see, you'll start capturing that missed area. Again, you'll never be perfect, but you will keep getting better. So that's integration actually says that the width of these boxes is infinitely small. That's the dx part. Okay. Dx or delta x is the width of these boxes. So one side of the rectangle. Numerical integration, instead of this being infinitesimally small, we say it has a finite value, 0.001 or whatever. Okay. So you're always able to take more boxes, and if you have a computer, you don't care that you take 10,000 boxes like this. It's just a simple for loop. It'll compute in seconds. All right. What happens if you start going volume? If you have 10,000 boxes on this plane, and now I tell you, all right, compute me the volume. You have to go in the third dimension as well. 100 times 100 is 10,000 in one plane. But if you do the same in volume, there's another 100 in there, okay? So how much is that? 1 million? Yeah, that's 1 million, right? So doing things in 2 dimensions is very easy computationally, but as soon as you start going in the third dimension, the problems, the difficulty increases substantially, okay? So there's again a limit on how many divisions you can make for the boxes. This used to be a problem, let's say 10 years ago. Today, you can do this on a simple laptop. So not really a huge problem. All right, perfect. So I'll tell you how to do all of this in a lot of detail. So it's very simple if you understand what's happening, but very, very useful. You can use this anywhere you want. Biology, you want to compute the volume of a cell. You use the same thing. It's irregular boundaries that you just cut up into these boxes. Economics, you want to compute how much profit or loss you made. You have the curve, you just integrate it numerically, you do the same thing. Okay. So let's see. Okay. Oh, stop it. All right, so that was the water plane area. If you remember, we were talking about stations, so taking this hull and cutting it vertically. That gives you different stations. Again, the submerged area is shown in red. You can do the same thing. You can use numerical integration to compute this. Midship station area is just you cut the hull at the midship plane. The submerged area is midship area. Okay. This is showing, all right, so this is basically showing what the area at different stations might look like. So starting at the front, station 0, you see the cross-sectional area here is nothing because you're at the very tip. So the value is 0. As you start moving back, the value starts increasing because the hull has a fineness ratio. Okay? It's pointy at the front, but it starts becoming bulky as we go towards the middle. That's why the area starts increasing and then becomes fine again at the aft. So the area drops again. Okay. And does it make sense why different water lines will give you different areas? So, you know, depending on how much you're submerged, your cross-sectional area will change. So that's when you're riding high in the water, that's when you're submerged a lot. Higher draft and lower draft. Higher draft means more distance submerged. Lower draft is more less distance from water line to keel. Okay, yeah, okay, that's another important thing. So this gives us an idea of which part of the ship is creating most of the buoyancy. The middle part of the ship has more dry area, so that gives us most of the buoyancy, okay? All right, so let's see. This is, I think we're more or less familiar with everything here now. Aft perpendicular shear, we don't care about. Midships, submerged load waterline, LP, LWL, LOA, okay? So that's the basic ways to describe what the hull geometry looks like. All good? Okay. Form coefficients are some, well, there's 3 or 4 different coefficients that you can look at the number and imagine what the hull looks like. Is it a very fine, slender hull, or is it a bulky cargo ship-like hull? Okay. For instance, the first coefficient that you might talk about is called the CW, water plane coefficient. You find the area of the water plane, shown in orange, and you find the area of this green box, the corresponding enclosing rectangle. You divide the two, and that's the water plane coefficient. LB, this is something that has to become natural to everybody. L is what? Yeah, it's given here. Is LWL in this case, okay? B is what? Beam, okay? So beam is maximum width going starboard to port. That's the rectangle, L times B, length times breadth, okay? And you see how different the number is for a destroyer versus a large tanker, okay? A destroyer has a slender shape, so you expect the red area to be smaller compared to the rectangle, 0.67, 2/3. For a tanker, it's more blocky, so 0.92. Okay. Describes fullness or fineness. Okay. Go. Block coefficient is talking about the same thing, but in terms of volume, not in area. Okay. What's the submerged hull volume? That's the one shown in red. And L times B times T. T is what? T is draft. That's the vertical distance. That describes the cuboid volume. That's called CB. Okay. Again, destroyer, only 45% of blocky volume. Tanker, 85% blocky. Prismatic coefficient is similar to this CB, but instead of taking a full rectangular block, you see the cross section in the front is a rectangle. In CP, the main difference is it's a more hull-like looking shape. And this cross section is the same as the mid-plane area. Okay. So where the at amidships, whatever your shape looks like, that's extruded forward and backward to describe the green box. All right. AM is area of midplane. Okay, fine. If prismatic coefficient is 1, that means you take the midplane, extrude it forward and backward, and the ship is exactly that. Okay, there's no tapering either forward or backward. That's what this last sentence is telling you. Okay, midship section coefficient CM, area of midship divided by this B times T. Beam times draft. Okay, that gives you CM. Fine, fine. All right, so look at this yacht, the numbers for the yacht. Block coefficient is 15% to 20%. Does it make sense? It's a very fine, slender hull. So fine, that's why it's very small. Prismatic coefficient is also the smallest. Midship area. All the coefficients are smaller because it's a fine hull. On the other hand, if you have the oil tanker, everything is very blocky and chunky. Midship area coefficient, look at this, almost 100%. Okay, block coefficient indicates this, fine, 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 okay. All right, so all of that we talked about. These are just some examples showing you the different values for the different coefficients. So here, CM, area of mid-plane, divided by B and T at the mid-plane. It's 1. Does it make sense why? When you cut the area at mid-plane, it will be basically a rectangle. Can you imagine that? So in that case, the ratio is 1. That doesn't tell us much, but the other coefficients will CB mostly will tell you how the hull changes. Hey, there's other hull forms shown here again. There's nothing complicated here, just computing the different coefficients. A more conventional hull, none of these numbers are easy to compute because AM, not easy to compute. Look at this, it's curved here. So you have to do numerical integration. Nabla, not easy to compute. That's the submerged volume. You have to do numerical integration. So there's no specific number, but we have to compute it. Numerical integration. Yeah, okay. All right. So the next thing I'll teach you is how to do numerical integration. But before that, let's talk about some static definitions of the state of the ship. So all right, can you see my ship here? Yes? Remote students? Look at my webcam.
Yeah, we can see it.
All right, so let's say the white part of the sail is the fore and the other part is the aft, okay? Ideally, well, not ideally, but usually you see everything is level, okay? If you have a slight roll, let's see, does it show up there? Okay. So this is level, and if you roll, if you see calm water, the ship is listing to the side, okay? This is called list, so rolling about the longitudinal axis. Why can this happen? Why can a ship or a boat list? So this is straight, this is listing. Nah, I wrote it on there. Too bad, okay. So let's say if you load on cargo and you're not careful doing it, you put too much on the starboard side. So there will be a moment, right? That's what causes a permanent list. No matter whether you're stationary or moving, you will have this list angle. On the other hand, if this is a more temporary thing, it's called a heel. If let's say you're sailing and there's a huge gust of wind from this side, it'll cause you to heel temporarily. As soon as the wind dies down, you'll go back to being straight. So that defines the sort of the roll angle, well, list angle or a heel angle. Trim is, okay, let's see. All right, perfect. So here everything is nice and level. And let's say you put too much cargo in the aft holds. So what happens is you'll trim like so, right? This angle is called the trim angle. And it can go both ways. It can be positive or negative. Drift is, I think it's better defined. All right, okay. So drift is, let's say your ship is angled, so it's going in, don't like this. All right. So right now the ship is sailing towards you, okay? But something happens and the angle deflects slightly, but it still keeps going towards you, okay? Straight along the vector pointing along my finger. The angle between, this angle in between is called the drift angle, phi, okay? Roll, pitch, yaw, if you're more, well, these are static angles, and dynamically we call them roll, pitch, and yaw. So roll is list, that's rolling about the longitudinal axis. Pitch would be longitudinal, changing angle about the lateral axis, and yaw is about the vertical axis. Okay. Okay, so yeah, that's what's mentioned here. Roll, pitch, yaw is the rotation in the three directions. And translation motion, surge is in the direction of the nose. Sway is moving side to side, and heave is up and down. That's all marked here. So surge is forward, heave is up and down, sway is side to side. All right. This one is very important, center of flotation, LCF. It determines a lot of stability characteristics. Have you, for your senior design projects, have you had to compute this, LCF? Okay, all right. So yeah, that's why we should teach this class before senior design. And we're trying to do that. So LCF is basically when your ship pitches along this straight line axis. So basically imagine there's a hinge rod that goes along this vertical dashed line, and the whole ship can pitch up and down about that hinge, okay? And this LCF is the point about with which that happens, okay? We'll learn how to compute this. It's the center area of the water plane. So you know how to compute the center of gravity for very strange shapes? So let's say this guy, again, look at my webcam. Don't say SolidWorks. How would you compute the center of gravity of this?
You take an element of the mass and you, again, you numerically integrate that by its distance from a fixed location, and that will end up, when you add those all up, you'll get a distance, or you get a coordinate of where your center of mass is.
Yeah, okay, okay. So, okay, let me, these two things, okay? Again, look at my webcam. It's a stapler and a boat. Let's say I glue the stapler to the boat. And I ask you, what's the center of mass of the composite object? How do you do that? This answer will help clarify what he was just talking about. So two things. I give you the mass of these individual centers of masses of these, glue them together. What is the combined center of mass? You don't have to do any numerical computation. It's a very straightforward one.
I think you do your, what is it, parallel axis theorem?
That's for moment of inertia, yeah.
Okay, yeah, you have a similar thing for your center of gravity.
Okay, so the center of mass would just be m1 r1 plus m2 r2 divided by total mass. You've seen that before, yes? R1 is center of mass of this guy, R2 is center of mass of that guy. M1 R1 plus M2 R2 divided by total mass will give you the location of the R composite, okay? So we do the same thing. If we have this funky object, which not straightforward, we break it up into small boxes and do M1 R1 plus M2 R2 for those large number of boxes and divide by the total mass. Okay, that gives you the center of mass of the composite object. Is it making sense? Remote students, tell me if it doesn't. I'll repeat it. These are very basic things that need to be bulletproof.
What is the difference between the center of flotation and the center of mass? Is the center of flotation on the hull of the ship, or is it embedded in the volume of the ship, like the center of mass is?
Okay. So, think about when you are, let's talk about the example I was giving earlier. So the question is, what's the difference between center of mass and center of flotation? The example I gave you earlier, if you start sailing from New England and go to the Caribbean and you refuel to the exact same specs, what has happened to your center of mass of the overall ship?
Shifts.
It shifts. Why do you say that? I'm telling you the cargo configuration is the same. The fuel tanks are the same, filled to the same level. The center of mass doesn't depend on the water, right? It just depends on the object. Doesn't matter if it's in space, in air, or in water. Okay? So it remains the same. Center of mass remains the same. What happens to the LCF? The LCF, well, the water plane will change, right? The ship will ride lower in the water. So the water plane the water line changes, the water plane shape will change because it's not a uniform hull. So the LCF will change accordingly. Okay, so the LCF depends on your water plane, but center of mass doesn't.
Okay, so just summarizing then, your center of flotation is always on the plane of the water line.
Yeah, it's the definition is here, and that's the second line shown here. It's the center of area of the water plane. Okay, so whatever cross section you get here, the center of area of that cross section is the LCF. Okay. Usually we measure the distance from the amidships line, but you know, it's not necessary. It can also be mentioned from one of the perpendiculars. Okay. And yeah, we'll stick to computing in 2D. Just be mindful that this is one component. We're looking at the top view, but think about the cross-sectional area. That also determines where it's located, right? Vertically. So that's what this is saying. Okay, so that was LCF, one very important point that we'll keep using again and again. There's an equivalent thing, you can call it the LCB, longitudinal center of buoyancy. B is just in 3D. If you talk about the same view from top, then we measure from the midplane, it's called the LCB. So B is the point through which all of buoyant forces will act. Okay, and the way you compute this is the center of volume, not the center of area anymore, is the center of volume. Okay, again, SolidWorks will give this to you, but the way you compute, how do you compute center of volume? So center of mass, I told you M1 times R1 plus M2 times R2. Do you know what I'm talking about? Let me just write this down so it's clear. And we'll do this in detail, but just to make sure everybody, how do I do this? Okay, so let me stop share for a second. No. Okay, then here. All right, perfect. So, come on, focus. Okay. So again, don't need to write this down right now. I'm just, because we will do this in detail. So center of mass is, let's say we have two objects here and they combine. This guy has center of mass there, and from an origin, we say this location is R1, the other location is R2. Okay. CM would just, and this is mass 1, this is mass 2. CM would be M1 times R1 plus M2 times R2 over M1 plus M2. And hopefully you've seen this before. Yes? Okay. Talking about mass. Same thing can do with area 1 and area 2. If it's a 2D object, you can say, well, I'll write down center of area. Area is what? What do you think it is? Yeah, it's A1 times R1 plus A2 times R2, or A1 plus A2. Okay. What center of volume? So what? Yeah, V1 R1 plus V2 R2 over V1 plus V2. Okay, so the same thing applies for mass, area, and volume. Any complex shaped object you have, you can use this principle to use and do numerical integration to find the respective values. Okay, and we will do that. All right. So instead of having this potato and this box, let's go back to webcam. Webcam is on, yeah. So instead of having that potato and box, look at my hull again, webcam. I can cut this up into many potatoes or many boxes and add them all up, similar to what I did here. Okay. That's basically numerical integration. That way we would find our B. So this would be exactly equal to B. Okay, that's the center of buoyancy. So it's the center of volume of the displaced water. All right, so LCB, distance from amidships to the center of buoyancy, is we call it LCB, longitudinal center of buoyancy. Distance from keel to center of buoyancy, we call KB. Okay, keel to B, KB. All right, where is it? Center, okay, fine. Yeah, KB is the keel. There's no transverse, like a TCB, transverse center of buoyancy, because you almost always the ships are symmetric, unless you're talking about an aircraft carrier. Okay. And there too, it's symmetric. The submerged part is symmetric. So yeah, there too. Okay. All right. We have 20 minutes, yes? 9:30, 10:50. Yeah, okay, perfect. So longitudinal moment of inertia. Do you remember moment of inertia from statics? Did you like moment of inertia in statics? Nobody seems to like moment of inertia in statics. It's a very, very simple thing, very, very straightforward, okay? You know, if you take an object and you try to push it, it doesn't want to move because of what? Because friction, fine, but friction is dependent on what? Frictional force, which depends on what?
Friction's dependent on the normal force, but I think you're looking for inertia, which is mass.
Yeah, so if something is heavier, more difficult to move because frictional force is larger, okay? So linear momentum depends on mass. Angular momentum depends on inertia, okay? That's the only thing you need to remember. When we talk about things rotating, we talk about moment of inertia. When we talk about things translating, we talk about mass, okay? So conceptually, the two things are equivalent, okay? And then again, you have to be careful. There's an area moment of inertia and there's a mass moment of inertia. So mass moment of inertia is what I was talking about. That if you want to compute what's the torque you need to rotate at a given angle, angular velocity, you need to compute mass moment of inertia. Area moment of inertia, instead of using mr squared, we use ar squared, okay? So that's intuitively, that's what you should think of, inertia being related to rotation, okay? How do you compute moment of inertia? So if maybe in your class you used tables? No?
You're just going to numerically integrate again.
All right, yeah. Okay, in your statics class, do you remember how you computed moment of inertia? Okay. That's related to a disk, okay? Do you remember BH cubed over 12 or L cubed over 3, things like that? So for very simple shapes, the value is straightforward. It's like an area of a rectangle, L times W, okay? But for a potato, it's not the same. The area is not straightforward to compute. You have to do numerical integration. Same thing here. Moment of inertia, you do numerical integration. So we have an IL, which is moment of inertia about the trim axis. So does it make sense why this is called the trim axis? The trim angle pitching up or down happens about this axis. So the hull rotates about this axis, nose up or nose down. Okay, we have, so one thing. This is called I longitudinal when it's across the transverse axis. Why? Seems flipped. The other guy is called I transverse when it's across the longitudinal axis. Why is that?
Because it's relative to your axis of rotation.
Okay. All right, what were you saying? Yeah, exactly. So the rotating about this axis is related to the longitudinal, well, yeah, it's related to the trim. So that's the longitudinal direction that we care about. In the other case, the rotation happens about the longitudinal axis, but in the transverse direction. So you're rolling to the clockwise or anti-clockwise. So that's why it's called IT, and the other one is IL. Oh, we've seen this before. Okay. All right. Okay. Okay. So another important term you'll encounter is displacement. Definition is it's the weight of water displaced by the body. When we are in equilibrium, what can you tell me about displacement? Ugh, I don't know why I write answers there. So when you're in equilibrium, the weight of the ship is equal to the displacement. Okay. If it's not, you will either rise up or sink down until this equilibrium is attained. Okay, ship's displacement influences behavior at sea. Okay, okay. So look at this. It's the weight of the water. Weight is Newton. Sometimes people will talk about the mass of water that's displaced. Then they'll use the term mass displacement. Okay, and this basically tells you the mass of the whole ship. Now, the ship itself consists of many different things. So if you only talk about the dry hull and the machinery, no fuel, no people, no food, nothing, it's called lightweight. Okay. Then we have dead weight. It's basically what you're carrying on board: people, food, fuel, cargo. That's all contained here, dead weight. So it's total displacement minus hull and machinery. Okay, but people are not useful unless you're on a cargo cruise ship. If you're on a cargo ship, you don't care about people. You want to maximize the cargo you're carrying, right? And minimize the fuel you have to carry, because that's useless weight, right? So where is the cargo dead weight? Oh yeah, so cargo dead weight is how much cargo you can carry, regardless of other things. Okay. All right, so that's most of the terms. Let's see. Yeah, I'll tell you a bit about numerical integration, but have you heard of this term, Froude number, FR? No, yes, where have you heard it? Air design, okay. Didn't learn it in fluid mechanics? All right, okay. So do you remember the Reynolds number? So Reynolds number is one of the most important non-dimensional numbers in fluid mechanics, okay? This is the second most important non-dimensional number in fluid mechanics. When you operate a boat or a ship, this Froude number will help you determine what's the, it basically helps determine the wave resistance. If you know how much wave resistance you have, it helps you determine how much fuel you should carry, or how big your engines should be, how much power should they output. So that's a term we'll use very frequently, again, later on. Definition is, it's the ratio of inertia to gravitational forces used to determine resistance of objects moving through water. Just like we use Reynolds number to compare a small model car to an actual car, so we can do tests on the small car. Same thing with Froude number. It allows us to test small models of a boat and to predict what would happen with the actual full-sized boat when we're designing these things. Okay, so this one looks familiar, yes, maybe, or forgotten. So celerity of the wave, the boats, you know, this is the characteristic wave pattern that the boats generate. It's called a Kelvin wave system. Okay, and yeah, all of this determines how much energy you're wasting. Think about this. These waves are nice to look at, but are they useful? They're not useful. What are the waves doing? They're what? Okay, they create resistance. In what way? I mean, it's not frictional resistance anymore. The waves are not rubbing up against the hull. So how do they contribute to resistance? What does it take to generate these waves? Energy. So you are wasting your energy in creating these waves. They are useless. That's where the wave resistance part comes in, okay? So ideally, you don't want to create these waves. Yeah. And yeah, I mean, depending on your displacement, your hull shape, and other things, the wave pattern, well, it's strange. Look at this. The angle is more or less the same between all of these very differently sized hulls. Okay. So Kelvin actually, well, somebody tried to say that the wave angle is always constant, regardless of the hull. But recently, people are not happy with that conclusion. So yeah, I think right now there's a debate going on. No, it's closer to 20 degrees, like 17 degrees or something. But again, I'm not sure. This doesn't look like 17 degrees. You're right. It looks like 45 degrees. I have to check. Yeah, I stopped following that when all this controversy rose up. Because right now we don't know. Okay. All right. Okay. Okay. Perfect. Let's see how much time we have. We have 8 minutes. Do we do integration now or no? Okay. All right, let's do integration next week.
What?
Do you have any questions?
Let's do it right now. I'm kidding. Okay,
if you buy rotten tomatoes and throw it at him, okay? Do you have any questions about anything? Homeworks, tests, quizzes? So wave mechanics people know everything already. We'll do the same, but others?
Is there any way you can post these slides like before class, just so we could write the little notes and comments you make on if we print them out? Or...
I'll do that. Yeah, I think I'm done with slides. There's one more. Let me see. Oh, okay. This one's on integration. So look. This is what I was talking about. You have these boxes. You can have one big box, or you can have many small boxes. And you see the approximation starts getting better. So yeah, I'll post these on Canvas. Well,
all right. Thank you.
Yeah. But that's it. And that's the last slideshow. Then.
Oh wait, so you'll start writing again like you used to, like the notes?
Yes.
Okay.
Yeah. But I'll put both today's and these 4 or 5 slides up on Canvas.
All right, thank you.
Okay, any other questions? All right, see you next week.
Have a great weekend. Thank you.
Bye.